Okay, so let's read 9.4. Do examples 10 and 12.
Like, you realize the assignment's just like...
I know. If I do this, then I'm giving you time to do it. Problems 29, 31, and 35. Okay. What we're going to talk about today are collisions that where the objects go off in two dimensions. They're not all lined up. So we're going to talk about two-dimensional collisions. First, let's review a little bit. Let's talk about collisions in general. Now, what we're really doing here is we're saying that during our idealized collisions, there really are no other forces involved here. Like when a car crashes into another car, a billiard ball hits another billiard ball, that, you know, the force of friction with the ground and all that is just going to be considered insignificant, or we're just going to neglect it. So here's what we said. Here's before a collision. I've got object 1 and object 2, and maybe object 1 is going really fast. Maybe object 2 is moving a little slower. And then after the collision, so this is before. Okay, and then after the collision, you know, maybe 1 is going a little bit slower, and then object 2 is really taken off here. So really what's happened is that object 1 has applied a force to object 2, accelerated it. Now it's going faster, but there was an equal and opposite force on this object, slowed it down a little bit, and so the momentum changed for both objects. But when you add up all those changes have to be equal to 0. Now I really want you to understand why. During the point of collision, or during the time interval where the collision is taking place, here's object 1 and 2, they are, again, applying equal and opposite forces to each other. This is the force of 2 on 1 is going to be equal, but in the opposite direction of the force of 1 on 2. And of course, these forces are applied for exactly the same amount of time. I mean, they're happening at once. So the duration of time where this force is applied is equal to the duration of time where this force is applied. And therefore, using the impulse momentum theorem, we know that if you apply a force for a period of time, that product is equal to the total change in momentum of the object. So this is the change in momentum of object 1 equals the change in momentum of object 2. But in the opposite direction, I lost a negative sign there from here, which means that the change in momentum of object 1, you add this to the other side, plus the change in momentum of object 2 is equal to 0. And what that means is that when you look at the overall system, there is no net change in momentum of the system. In other words, P initial equals P final. If you consider this is the sum total momentum in our system before the collision is equal to the momentum sum total that I have after the collision. And this is where we start. This is how we solve problems. Now, in all the problems that we did before, everything was along a straight line. But in fact, this is a vector equation. And it applies in 2 and in 3-dimensional space. So when I say that P initial equals P final, I can break that up into its X, Y, and Z components. Now let's just do this in 2 dimensions. Let's not worry about the Z direction. Let's just talk about if I say P initial equals P final, well, I can say, well, look, P initial has a X and Y component. So P initial is equal to P initial in the x direction plus P initial in the y direction with those, unit vectors associated with it. And this is going to be equal to P final in the x direction plus P final in the y direction, or the y component. So here are the momenta split of the whole system, but this represents the momentum in the x direction, and this represents the momentum in the x direction before and after, and they have to be equal to each other. So what we can do is say, look, this has to be equal to this, and this has to be equal to this. And so what we're going to do now is split the problem up into the x direction and y direction, and we can solve them separately. It's a little more complicated. I mean, there's more work to do, but it's the same basic idea. So if I look in the x direction, well, let's say I have two objects like this. Here's object 1, and here's object 2. And object 1 is moving along a path like this with a certain velocity, certain momentum. Let's say object 2 is at rest. Let's just make it simple. Well, here we're going to have a glancing blow. The force, while they're colliding, so this is the before picture. Now let's look at the during picture. During the collision, here's object 1, and here's object 2. And you can see now that the interaction forces between them are not aligned with the direction of motion of object 1, but in fact are like this. Now, don't confuse. This is not a force vector. This is a velocity vector here. But these are forces. This is a force of 2 on 1, and this is the force of 1 on 2, and they're equal and opposite. But look, if this object is moving this way and we get a net force like that, and from your personal experience with this stuff, that object 1 is going to move off in a direction that's kind of like this. So there's its velocity, and this object is going to get pushed in this direction. So both objects are going to get, so this is before, during, and after the collision. And these are the velocity vectors. This is V1 final, and this is V2 final. But these are vectors. They have directions associated with them. Well, if I'm given a problem like this, I can set up the equations this way. I can say, well, first of all, in the x direction, P initial in the x equals P final in the x. And this lets me say, okay, well, what is the initial momentum in here? Well, if I look at this particular example, before the problem started, in the x direction, it's just M1, we'll call this V1 initial. I mean, it was moving all in the x direction. And so that's got to be equal to M1 V1x final. Now, here we get really into a lot of subscripts. Now, what do subscripts do? Remember, they just describe what it is we're looking at. And this has, here's my vector V1, but remember, it has an x component and a y component. So it all depends on what angle this is. So V1x final, you have to use is V1 final times the cosine of the angle that it comes off. And then this is going to be plus M2 V2x final. I mean, object 2, the x component after the collision. So you need 3 subscripts to describe this particular velocity. It's a component. Okay, it's for object 2, and it's after the collision. So that's 3 things you have to describe about it. That's why it has 3 subscripts. So don't be intimidated by that. It's just a way of describing it quickly. Well, this gives us an equation that we can, that we can use to solve a problem depending on what's given. Okay? Then I can also go, P initial in the y direction equals P final in the y direction. Well, this is kind of nice. If you set up the problem like this, how much momentum is in my system in the y direction before the collision? There isn't any. So, yay! The initial is 0. And this is going to be equal to M1 V1 y final plus M2 V2 y final. Okay, so let me zoom in. It's kind of small, isn't it? So now, here is an equation now that lets me solve problems. You may have to use these two. And remember that there is another variable here, and that is the angle that these things come off after the collision. So you need to know what these angles are, and they're not necessarily the same. We'll call this V1, theta 1 and theta 2. So, and you have to account for the direction. This is going down, so V2 final in the y direction is going to be negative, and V1 final in the y direction is going to be positive. You have to have a positive and a negative quantity in order to get to 0, right? So these two are going to be equal to each other. So these are kind of the basic ideas you need to solve problems in 2 dimensions. So when you solve the problem, first of all, you need to establish an axis system. You need to establish what direction is x and what direction is y. And you know what? It's just kind of like what we did when we were doing the procedure using force and free body diagrams and so on. You can choose your x and y axis to make the problem easier to solve. So if I had a problem where what was given, if they gave me a problem like this, these objects are moving like this, and they're going to come off at angles or whatever. Well, yeah, they gave me the drawing that looks like this, but guess what I'm going to do? I'm going to make this my x-axis. Why would I do that? Because it just, in the y direction now, y direction is perpendicular to this, there's no momentum initially or at the end. So it just makes the problem a lot easier to solve. I don't have to break it up into components as much. And then just recognize that the momentum in the x direction will be conserved, the momentum in the y direction will be conserved. These x and y components of the velocity vectors you just get from the right triangles you write, for those final velocities. Okay, and you can do it. So what I would like you to do now is example 10 on page 268. Please do that right now, and so you get a sense of how to solve these problems. Also, on page 268 of your book, they have problem-solving hints, 2-dimensional collisions. They have a kind of a procedure, a problem-solving procedure for solving these. It's really good. So read that and do example 10 right now, please. Okay, go.